This is lecture 3H for Calculus 1 on implicit differentiation. In implicit differentiation, the operator, the differential operator d by dx, is applied to both sides of the equation. Up to now, we have written equations with the dependent variable isolated. That means we've written y equals something, and all the x's or all the t's were on the right-hand side, and all the y's were on the left-hand side. And in a sense, we did apply this operator to both sides of the equation, but it just seemed at that time like notation. So if I start with something y equals x to the fifth, okay, now the y is isolated, and every term that involves x is isolated on the other side of the equal sign. I applied the differential operator to both sides. We didn't think about it, but that's what we were doing. On this side, we got dy by dx, because that's all there was to do in evaluating it. There was nothing to evaluate. On the other side, we could take the derivative of x to the fifth and get 5x to the fourth. Sometimes that we can't do that kind of isolation. For example, with this equation, how are you going to isolate y? You can't do it, right? So here, the dependent variable cannot be isolated. You cannot write y equals or f of x equals, but we still can take the derivative if we use implicit differentiation. To use that, we apply the differential operator to both sides as before, but this time we have to carry out the differentiation on both sides, then isolate the dy by dx. To use implicit differentiation, you have to remember the chain rule. Okay, here I'm going to use y because that's how we wrote it. Say y is the result of composing f and g. Right? To take the derivative of y, we would take the derivative of the outside function and evaluate it at the inside function, multiply it by the derivative of the inside function. Or we could write things in terms of u. Say y is a function of u and u is a function of x. Then if I take the derivative of y with respect to x, so I'm going from all the way from y through u, trying to get to x, then I take the derivative of f with respect to u, then I take the derivative of u with respect to x. Now let's look at the power chain rule again, but this time remember that u has not been specified. So I want to write just a formula for this where u could be anything. So the inside function could have any form. So I have the derivative with respect to x of, say, some function, I don't know what it is, u, raised to the power n. Well, something to the power n is the outside function, so I take its derivative and evaluate it at u. So I get n times u raised to the n minus 1. Now I still have to take the derivative of the inside function, but since I don't know what it is, I just leave it in this form. In implicit differentiation, this is the form that you're going to see at the end, and the u will be replaced by y. For example, if I wanted to take the derivative with respect to x of y to the n, I would first have to take the derivative of the outside function, which is something to the nth power, and I would get n times y to the n minus 1. Then I have to take the derivative dy by dx. Now dy by dx won't be evaluated, instead we'll just solve for it. Okay, I want to give another example of this. Say you want to take the derivative of sine u, and you aren't specifying u. In this case, the outside function is sine, the inside function is u, the unknown function. Well, to carry out the differentiation, I take the derivative of the outside function. The derivative of sine is cosine. Okay, write that there. And multiply it by the derivative of the inside function, du by dx. If I don't know what du by dx is, I just have to leave it there. If I want to completely finish taking this derivative, I would either have to know what u is or I would solve for it. In implicit differentiation, you'll have similar terms. You might have the derivative with respect to x of sine y. I don't know how y varies with x. Maybe it's buried and hidden somewhere, but I can carry this step out. The outside function is sine. I take its derivative and evaluate it at y. There you go. Then I multiply it by the derivative of y with respect to x. So I'm going to carry this out for the function x cubed plus y to the fourth equals 14x. All right, first of all, this is not a function. It is just an equation. If I were to isolate y, I would have to take the fourth root. I would end up with 14x minus x cubed and take the fourth root. Well, for even roots, there's always two answers. One has a positive sign, one has a negative sign. As a result, this is not a function, but I can still carry out the differentiation. Right. To do that, I apply the operator d by dx to both sides of the equation. Right. On the right-hand side of the equation, derivative with respect to x of 14x is just plain old 14, so I can write that there. That's done. On the other side, I have to do a couple steps. So what I have on the left-hand side is the sum of two terms. The differential operator I can just take this derivative of the first term, which is x cubed, and get this answer. That's done. Now, how do I take the derivative with respect to x of y to the fourth? We have to use that chain rule, the chain and product rule together. So this is as though you had a composite function. The outside function was x to the fourth. The inside function is the unknown y. I take the derivative of the outside function. Something to the fourth is 4 times something cubed. Okay, then I take the derivative of the inside function, which is dy by dx, only it's not specified. That's fine, and I solve for it. So here I solve for it. Dy by dx, which is what I was after, equals 14 minus 3x squared divided by 4y cubed. I guess y better not be 0, right? You can see here that in this case y appears on the right-hand side. That is because this is not a function. In other words, the graph for values of x would have more than one value of y. In this case, well, two values of y in this case. So you have to know where you are on the curve to get the derivative. That works better with a picture, and I'll show you one in a minute. So let's go again. I just want to go through these steps again. That off. I'm taking, I want to get the derivative dy by dx of the expression, from the expression x cubed plus y to the fourth equals 14x. I apply the derivative operator to both sides of the equation. On the side where there's only the x, I'm fine. Just carry out the derivative with respect to x. On the other side, in this case, I can use the addition law for the derivative, and I'll take the derivative of 3x cubed and get, x cubed and get 3x squared. Okay, that's done. When I try to take the derivative of y to the fourth, this is as though I'm taking the derivative of a function that has been composed. The outside function is something to the fourth. The inside function is y. It's unknown, but I can still deal with it. I take the derivative of the outside function, and I get 4y cubed. Then I have to take the derivative of the inside function, in that case dy by dx. I don't know what it is, and I'll find out. The way I find out in this case is to solve for it. With this example, you'll see now why sometimes this y appears in the derivative and it's needed. So here I have equation for a circle. X squared plus y squared equals r squared. I want to take the derivative. Apply the derivative operator to both sides. On this side, which is the right-hand side, r squared is a constant. The derivative of a constant is 0. That's done. Okay. Over here, I apply it to each term. The derivative of 2x squared is 2x. That's done. When I apply the derivative operator to y squared, I remember that this is a result of composition. It's a composition of something squared composed with y. Right? I take the derivative of the something squared and get 2y. That's done. Then I take the derivative of the inside function, which is dy by dx. Then I solve for dy by dx, and I get x equals minus x over y, and y cannot be 0. Again, to evaluate this derivative, because y appears on the other side of the equal sign, you need to have values for both x and y. And you can see now when you look at the graph of a circle why this is reasonable. Okay, so we had the function, or rather the expression, x squared plus y squared equals 100, which is the equation for a circle. So we found that the derivative dy by dx equaled minus x over y. Right. When you want to know the derivative, you need to specify both the x and y. If I take the derivative at 6 and positive 8, it'll be right here, the slope is minus 4/3, because as you're coming down this part, remember slope, the sinus slope has to do with progressing towards positive x, towards increasing positive x. So you're coming down the curve this way, the slope is negative. What's the slope on this side? It's positive, it's 4/3. So it depends where you are on the curve, what the slope is. So for figures that do not represent functions, you will end up with y, the dependent variable, as part of the derivative, and that's okay. So to reiterate, we used implicit differentiation when we do not have the dependent variable separated out on one side of the equal sign. Okay, and then when we carry out the derivative, we just apply the differential operator to both sides, work through the problem. We'll end up with the term dy by dx, and then we isolate dy by dx. Sometimes the y appears in the derivative, and that just happens to be because the graph is not the graph of a function, and you need to know where you are in the figure in order to compute the derivative. Notice that y was not 0, could not be 0. If y is 0 on this, and for the circle, you would be right here. And what's the derivative? Well, that would be a vertical line. It would be infinite, and we don't allow derivatives that are infinite. So excluding y equals 0 is just excluding those 2 points right there.